All right, this is Chemistry 150, organic and biological chemistry. Today, what we're going to talk about is isomers, and we're going to talk about constitutional or also called structural isomers. So isomers is it's not a large part, but it is a major part of organic chemistry, especially biological chemistry, where one isomer can be beneficial to the body and another isomer can be deadly to the body. So what are isomers? Well, isomers are substances that have the same molecular formula but different structural formulas. So let's look at C6H14. All right. So the first thing that you should do is when you look at this compound, or this formula or compound, either way, is do you think think about what classification this is? So it looks like it's an alkane, right? Because alkanes take on the form of CnH2n plus 2. So N in this case is 6. 6 times 2 is 12. 12 plus 2 is 14. All right. So probably the first substance that comes to mind is to just put the 6 carbons in a chain like so, and then attach hydrogens like so. All right, so we got 1, 2, 3, 4, 5, 6 carbons, and we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And there's my 14 hydrogens. And so you look at the longest chain here and you go, oh yeah, this is hexane, an alkane. So we would name it hexane. All right. Now, what if we made this only 5 carbons long, and then we attached a carbon to this second carbon here? So again, hydrogens here and hydrogens here. Let's count them up and see if this works. 1, 2, 3, 4. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, C6H14. They both have the same number of carbon. They both have the same number of hydrogen. But this is definitely not the same compound. The longest chain is only 5 carbons long. So it's a pentane. So again, the way we would name this is this is a methyl group attached to the second carbon, and so we would number this in the lowest numbers possible. So 2 would be the correct number. So 2-methyl pentane. All right. Now, another thing that can happen here is, let's say I took this methyl group off and I put it over here on this side. Is that the same compound or a different compound? Well, it is the same compound. In fact, if we flip this around, it would look, if we just picked this up and flipped it around, it would look just like what we had before. So this is the same compound. So this is also 2-methylpentane. So there's no difference here. This is not, there's not 2 isomers of 2-methylpentane. I mean, these are same things. Now, what makes this an isomer? You can't take this compound and it overlap that. You know, this doesn't superimpose or just fit perfectly over the hexane. They are 2 different compounds. They do have different chemical and physical properties. All right, what's another choice? Well, instead of putting this methyl group on one of the second carbons, let's put it right in the middle like that. And again, what we've done now is this is a tertiary carbon, right? It's got 3 carbons attached to it, where this other one, well, it would have been tertiary too. All right, so you get something like that. Now that's a different compound. This compound now becomes 3-methylpentane. 3-methylpentane. Okay. So now we've got 3 isomers that we've done. We've done hexane. We've done 2-methylpentane. And we've done 3-methylpentane. Are there other ones? Can you think of some other ones that are possible? All right, well, we've run out of room on this side, so let's go to the next slide. What if we made the carbon only, the longest chain only 4 carbons long? And we put a methyl group here and a methyl group here. All right, so let's fill in our hydrogens. And these are separate here, and these are 2 separate. This is a methyl group here, and this is a methyl group here. All right, so now we're no longer talking about this in terms of a hexane or a pentane. The longest chain is this chain here, and it's 4 carbons long, so it's a butane. All right. And the methyl groups are at the 2 and 3 position, so you would say 2, 3 dimethyl butane. 2, 3 dimethyl butane. That tells the person there's 2 methyl groups off of the chain. And what positions are they? Well, they're 2 and 3. This is carbon 1, 2, 3, 4. All right, can you think of another one? What if we take this methyl group and move it up here? So we still have a 4-chain long hydrocarbon. That's the backbone. But now, off one of the carbons, we have 2 methyl groups. All right, so it's still a hexane, it's still dimethyl, but this would be 2, 2, 2, 2, 2 dimethyl butane. All right. Are there any others? What if we made this a? What if we made this an ethyl group down here, where the 2 carbons are connected, so we get something like that. All right. So let's look at that. So would you be going? You'd go 1, 2, 3, 4, and you go, oh, it's a butane. But wait, this is where everybody makes a mistake. This is no longer the longest chain across here. The longest chain starts 1, 2, 3, 4, 5. So this is not a butane. This is a pentane. 1, 2, 3, 4, 5. So this is a pentane when you do this. And then we look and see where this methyl group is attached. It's attached on the 3rd carbon. So this is 3-methyl pentane. Yeah, I'm trying. I tried to cheat there and just connect it up. 3-methyl pentane. Well, we've seen that before, right? Let's go back to the previous slide. Right there it is, 3-methyl pentane. So you got to be careful when you're doing structural or constitutional isomers. It's tempting to do something like that. But again, if that makes this the longest chain now, this is actually the same thing as 3-methyl pentane. All right. So in the end, we had 5 isomers based off of C6H14. So 5 isomers off C6H14. So that's what you have to do. I would encourage you to do the problems in the back of chapter 10 that talk about isomers, and it's kind of like a puzzle. That's the way you want to treat it, where you're given this and they say make as many compounds out of it as possible, and you start manipulating it. If you're having a hard time with looking at the isomers, you may want to get a model set, a cheap model set, and actually make models of these so that you can actually physically see them and hold them and see how they are different in three-dimensional space. All right. Another type of isomer are called cis and trans isomers. And a cis and trans isomer might look like CH2. This is about the simplest one that I can draw. It may look something like this, and you go, okay, so let's put this together. You know 2 carbons are bonded together, and you know there's a hydrogen, and you know there's a hydrogen. Oops, I made the, let's see, did I make a mistake here? Yeah, I want to call this C2H2Br2. All right, and then 2 bromines like so. And so we're trying to do a little structure for this. Let's do that. Let's add up our total number of valence electrons. So 2 carbons, that's 8. And then the hydrogens, each one has 1, that's 2 more. And then 2 bromines, each one has 7 valence electrons, that's 14. So we're dealing with a 24 electron system. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then each one of these lines represents 2. So that's 14, 16, 18, 20. And what we don't have, and there's 22, and 24, we're going to have a double bond on that carbon. So that carbon feels like it has 8, each bromine feels like it has 8, and the hydrogens feel like they have 2. All right, so the thing about a double bond is that it's fixed rotationally, that this carbon can't circle around and freely, and this carbon over here can't circle around the axis freely. So what happens is you either get, when you have this dibromoethene, the problem is that you either have this compound, or you have a compound where the bromine is on this carbon and the bromine is on this carbon across from each other, like so. All right. So these have the same chemical formula, but they have different structural formulas. And again, this is the property, like one of these may be beneficial to the body and the other one's not, so we have to be able to differentiate between these 2 isomers. So these are isomers, same chemical formula, different structural formula. And the reason why these are structural is that, again, there's no rotation around these carbons, so it's fixed because of the double bond. And so these don't interconvert from one to the other very easily. So this one where the 2 bromines are beside each other, this is called a cis isomer. Cis isomer. So this would be cis dibromoethene. All right. This one over here would be the trans isomer. Transatlantic across from each other. So that's what this one is. This is beside, cis is beside, and across from each other we call a trans isomer. All right. Now your book, it really doesn't bring in those double bonded isomers yet. What it does is it talks about they talk about cyclohexanes, because we're still really focusing on the alkanes here. So what we have here is we could have hexene, hexane. Let's do this, cyclohexane. All right, what does cyclohexane look like? Well, it's 6 carbons. All right, so there's 6 carbons. Carbon 1, well, wherever you want to name 1, 2, 3, 4, 5, 6. All right, and so that would be C6. Now, what happens when you have a cyclo? What happens to a cyclohexane? What happens to the number of hydrogens? Well, they decrease because all you can have is 2 constituents off of each carbon, because there's already 2 single bonds coming off each carbon. So you're going to get something like C6H12 as the chemical formula for a cyclohexane. So the general formula is CnH2n. All right. So because this is in a ring structure, and even though it's a single bond, these bonds are fixed. They can't rotate very easily. So because they can't, we again have a cis and trans isomer. One would be where the bromine is across from each other, like so. And then the other isomer would be where the bromines are on the same side. So you have a bromine here and a bromine here. Okay? So if they're on the same side, this is the cis isomer. If they are across from each other, that's the trans isomer. So this would be trans 1,2 dibromo cyclohexane. And this would be cis 1,2 dibromo cyclohexane. All right. Now, another thing that can happen here is you want to show this in a simpler form instead of drawing. You want to show some structurality, three-dimensional structure of these compounds. So here's another way you'll see this written. You'll see the ring structure like that for cyclohexane. And then what you'll see is you'll see one bromine coming out at the board at you. That's usually just a triangle like this. And then one bromine going back through the board like that. When you see that, that's trans. Whereas if I want to show both of these as cis, I'd probably just show 2 triangles like this. And so, again, what's the difference between these two? When you have this dashed like this, this means that it's going behind the plane. So it's behind. So we kind of flip this on its side, like you're drawing it here. And the bromine that has this triangle is coming out at you outside of the board or the plane, and the dashed line says it's going back behind the board or plane. So that gives you that trans configuration, that they're across from each other. Whereas both of these are coming out at the board at you, so they're both on the same side, so that's the cis isomer. So that's how you show it. If you want to show three-dimensionality on two-dimensional paper, dashed lines or dashed triangles mean going back behind the plane, and solid triangles, or at least an outline triangle like so, represents that it's coming out of the plane towards you. All right. So from that, you can determine cis and trans. All right, let's talk about conformations. This is going to be specifically for the cyclohexane, and then when we get into, so when we get cyclohexane, we get something like this. All right, so there's my my hexagon. It's not the best. They should all be what, equal sided. All right, so if I have cyclohexane and I add energy to it, I can get a structure that looks like this. And when I get this type of structure, it's called the chair conformation. All right, and because it looks kind of like a chair, lounge chair, where you have this and then like that and like that. So this is called the chair conformation. And that is generally one of the more stable configurations, because if we would look at the hydrogens that are here, they're more so in their own space than again, because remember, these are actually kind of coming off like this. This one's actually, generally the convention is this one's going down and this one's going out, this one's going down, and then it's going out like that. So you can look at these. This is on page 350. They give you a better picture of this. Or you can just Google chair conformation of cyclohexane. You see much better models than what I'm drawing here. But the reason why this is the best, lowest energy model is because there's less interaction between these hydrogens and hydrogens on the adjacent carbon, because they're in their own space. Now, what can happen is this part of the cyclohexane can bend upwards, and you get something like let's see, how do I do this? Something, I don't know if I can. Oops, made a mistake there. What happened? Let's see, 1 2 3 4 5. Yeah, I guess what I want to do is something. I'm not the best drawer like this. Let's see. Yeah. So let me let's try it again. You got the two triangles, and then you have this, and then that, like that. All right. Let's try it one more time. All right, so let's go. 1 2 3 4 5. Oops, I need another carbon. Let's see. 1 2 3 4 5. Yeah, I need another carbon here. One, two, three, 4, 5, 6. Not my best drawing. Let's see. And there's a better way to draw this. I probably should have looked something like this up. 1 2 3 4 5 6. All right. And this is called, if you look at it, it looks like a boat conformation. Oops. Now this one, again, there's more energy in this conformation because the carbons do come in closer contact with each other, and there's a lot more interaction between, not the carbons, but the hydrogens come in closer contact with one another. Actually, the carbons do too, because they're bent upward. You're going to get more interaction here between each carbon. You've caused the ends to tip towards each other. And so this boat conformation requires energy for this to happen. And yeah, at room temperature, there's enough energy for this conformation to occur. So you do get some oscillation between the boat conformation and the chair conformation. All right, so these are called conformations. That's what you need to know, conformations. And the two most common, chair and boat. All right, last slide, we're going to talk about a couple of reactions that happen with alkanes or hydrocarbons. The main one that I want you to know is combustion. Actually, there's two here that you need to know. Combustion is one. The other one is where we have a halogenation. So combustion is anytime you burn a hydrocarbon in pure oxygen. So this is butane, like a butane lighter. You always get as products carbon dioxide and water. All right, that's what you need to know. Anytime you burn a hydrocarbon in pure oxygen, you will always get carbon dioxide and water as your products. So then it's a matter of balancing the equation. So again, the way we would balance this, I would look at that. It says 4 carbon. I'd put a 4 there. And then I would look at the hydrogen. It says 10 hydrogen. I know I've got to put a 5 here. 5 times 2 gives me 10. Then I'd add up the total number of oxygen on the product. So we got 4 times 2, which is 8. And then 5 times 1 is 5. So we got 13 oxygen on the product side. And so then red flag shows up because this is an odd number here and this is an even number here. The quick way to fix this would say 13 halves, like that. These 2's will cancel out and that'll give me 13 oxygen on both sides. So you could do it that way, or you could multiply the entire equation by 2 and you would get 2 butanes plus 13 oxygen yields 8 carbon dioxides plus 10 waters. All right. So you can practice a couple of those. I mean, the main thing is that anytime you burn a hydrocarbon and pure oxygen, you will always get carbon dioxide and water. This is called a combustion reaction. All right, the next reaction we want to talk about in this chapter is a halogenation. So we take something like methane and we add bromine to it, and then we add heat or light. So you got to have some type of energy in the form of heat or light to cause this reaction to occur. So what happens, this is a substitution reaction where one of the hydrogens is knocked off and in its place a bromine is added. And so we would get bromomethane plus hydrobromic or hydrogen bromine. Yeah, since we're not, here's the key right here. Since we're not in a water solution, this is not hydrobromic acid, it's hydrogen bromide. So there's something to remember, that we are dealing, a lot of times in organic chemistry, we are dealing with non-aqueous systems. And the reason why is because, remember, these hydrocarbons, these alkanes, are non-polar. So if we tried to mix them with water, they would not mix. They stay separated, just like you know, oil and water do not mix. So we're working in a non-aqueous environment, and this substance, it may look like hydrobromic acid, but it's not an acid until it dissolves into water and forms the hydronium ion. So this is hydrogen bromide over here. Now, the more bromine we have and the more light we add, this substitution can go on, so we can get something like a dibromomethane or a tribromomethane or a tetrabromomethane. That's where we get something like tetra. Remember when in Chemistry 1.4 we talked about carbon tetrachloride. So that was an ingredient in dry cleaning many years ago. And another thing that can happen is, again, you can get different compounds. Like, what if we have a long chain? Maybe we'll put a methyl group here. What happens when I add bromine to that? Or let's change it up. What if I add chlorine to that? Well, you're going to get some compounds where the chlorine group is here. And you'll get some compounds where the chlorine group adds to the end carbon. And you could get other compounds. I mean, you could get one where, I mean, if we add the chlorine to this end, it's the same as this compound, right? But we could get other compounds besides these two. All right. So the main thing here is halogenation reactions. You take a hydrocarbon, alkane, you add a halogen to it. Remember, this is diatomic. That's the way they naturally occur in nature. If you don't remember what elements occur naturally diatomic in nature, Hahn, Cliff, Burr, these are the elements that naturally occur diatomic in nature. All right? And again, this is called a halogenation reaction. You must have lighter heat for this reaction to occur. And it's a substitution reaction where the bromine knocks off a hydrogen, or in this case down here, it knocked off a methyl group. Oops, I don't know if that's actually what I should show here is that it knocked off a hydrogen here, and the methyl group stays on. Yeah, my mistake. All right. So that concludes chapter 1. This isomers, this is something to focus on, and also the two reactions, combustion and halogenation. If you have other questions, please email me. Thank you.